Hello, my name is Robert Vesztek. I'm an associate professor at早稲田University. I teach several courses related to economics and game theory at the School of Political Science and Economics. Let me say some words about my educational background first. I did my undergraduate studies at the Budapesti Közgazdaságtudományi Egyetem, that translates to the Budapest University of Economic Sciences. My major was economics, and I specialized in actuarial sciences and applied statistics. After graduation, in 1999, I decided to continue my studies, and I went to graduate school in Barcelona at the Universitat Autònoma de Barcelona. I was a student at the International Doctorate in Economic Analysis. First, in 2001, I earned a master's degree in economic analysis, and later in 2004, I completed the doctorate and I got a PhD in economic analysis. The title of my thesis was Auctions, Mechanisms, and Uncertainty. I was analyzing both theoretically and empirically mechanisms designed to extract private information from economic actors. I started my academic career as a teaching assistant back in Budapest, at the Budapesti Közgazdaságtudományi Egyetem, and I also taught several courses during my PhD studies in Barcelona. Later, after the PhD, I was an assistant professor at several places in Spain, and also I spent a short semester at Osaka University here in Japan. I joined Waseda University as an associate professor in 2010 when the Edessa program started. And I have been teaching game theory, experimental economics, microeconomics, and various seminars on economics ever since. But it's not only teaching that we, university professors, do. We also spend quite a lot of time on research. When it comes to research, I tend to use the experimental method to analyze questions from microeconomics and game theory. On the screen right now you can see a short list of publications. They are similar in a sense that they are once again dealing with problems with asymmetric information. They are looking at problems of how to extract private information from economic actors, but they are dealing with slightly different problems. The first one, choosing a common project, experimental evidence on the multi-bidding mechanism, that I wrote with my PhD supervisor, David Perez Castrillo, looks at a classic economic problem, the problem of choosing a common project. The next is more related to political science. That's also a joint with Agnes Pinter. In that paper, we analyze, again with the help of experimental economics, the conflict that may arise between the minority and the majority, and the society is using, for example, the majority vote to make certain important decisions. And the third paper, again a joint work with Joanna Pais and Agnes Pinter, is using the experimental method to understand how certain mechanisms from matching theory perform under different scenarios in terms of information. But let's not only talk about myself. In the second part of this video, I would like to invite you to a small challenge. Okay, so for the sake of this challenge, please imagine that there is $100 to be divided between you and your partner, according to the following procedure. Each of you will claim some amount not greater than $100. Later, the amount that you will receive depends on the sum of your claim and your partner's claim. Please note the following two rules. One, if the sum is greater than $100, both of you will get nothing, $0. The second, if the sum is less or equal to $100, then you get what you claimed and your partner gets what he or she claimed. You may want to stop this video, read the rules again, and sit back and think a little bit about this interaction. What I would like to know is, what is your claim? Imagine that I'm your partner in this situation. Okay, so I decided to claim $40. Of course, unfortunately, I don't know what exactly your claim is, but let's imagine, for the sake of my explanation, that as most people, you claim $50. If that's the case, according to the rules, we would compute the sum of my claim, $40, and your claim, $50. That would give us $90, which is strictly less than the available $100. So each of us would get the amounts that we claimed. You would get $50 and I would get $40. But is that the only reasonable amount to claim? Couldn't you or couldn't I do better by claiming somewhat more? Or maybe by claiming somewhat less? In order to answer these questions, let's turn to game theory. Game theory offers very useful tools to understand strategic interaction. We might also call game theory as the theory of strategic interaction. Let me explain this term. Okay? So, if you think back of the previous example, each of us had to choose a certain amount of money as a claim. We call these amounts as strategies, chosen by one or the other person. And of course, there is interaction. Why? Because, for example, your satisfaction, your gains, your earnings at the end of our game will not only depend on your choice, on your claim. It will also depend on my choice, my strategy, my claim. Whenever we have such a situation, whenever we have a situation of strategic interaction, we are talking about games in game theory. Maybe the word is a little bit misleading. So, for example, Robert Aumann, a famous game theorist, suggested that we might want to call game theory as interactive decisions theory instead. Let me quote him. He says that the term game theory stems from the formal resemblance of interactive decision problems, that is games, to parlor games. The term also underscores the rational, cold, calculating nature of the analysis. So what we usually do in game theory is to look at situations, conflicts of strategic interaction, and we try to figure out what rational, cold, and calculating people would do. Game theory itself was born in 1944. That's the year when the book by Morgenstern and von Neumann, The Theory of Games and Economic Behavior, was published. Of course, strategic choices and strategizing had existed well before 1944, but we consider this year as the year of the creation of game theory. I will spare you the mathematical details in this talk. Let's just try to imagine the situation with the help of a simple graph. You see now a purple bar on the screen in front of you, whose height is exactly 100 units. Those units represent the $100 that are available to split between you and me. As I told you, I decided to claim exactly $40. That's what appears now in a lighter shade. So if I decide to claim for whatever reason $40, I create already a split of the available amount of money. My claim, the $40, will also define the leftover, that is $100 minus 40, that is $60. And the partner's claim, my claim, introduces, you will see, an important threshold to this analysis. And that threshold, exactly at the height of $60, appears now with the dashed line on your screen. Why is this important? Well, let's think of the typical claim that most people would choose in this interaction, $50. So if that is your claim, it is located slightly below the $60 threshold. My question is, can you do better? In game theory, we assume that you would like to maximize your satisfaction or your earnings in this interaction. In this simple game, I think it's safe to assume that what you would like to maximize is your monetary gain. So I hope you can see, with the help of this picture and my previous explanation, that claiming 50 in an interaction with me, who is claiming 40, is not the best you can do. By claiming somewhat more, for example, $55, you would be earning $55. Why? Because the sum of my claim 40 and your new claim 55 would be $95, which is still strictly less than the available amount, $100. I would be still earning 40, but you would be earning, in this case, $55. So you do have incentives to increase your claim somewhat. But you have to be careful. Let's see what is going to happen if you pass the $60 threshold. For example, in this situation, you are claiming $80. That's just too much. Why? Because if my claim is still $40 and your claim is now $80, the sum would be $120, that exceeds the $100 limit. Therefore, both of us would end up gaining nothing, $0. You don't want to reach such a situation. I hope you can see now that the best you can do, given my claim, given your partner's claim, the 40, is to claim exactly the leftover, exactly $60. And of course, you can turn this story upside down, right? So, given your claim, $60, the best I can do, the best your partner can do, is to claim the leftover, that is exactly $40. In a sense, we are in a stable situation that we can call as an equilibrium. Let's look at this graph. So this graph will be useful to represent the equilibrium of this interaction. Now on the horizontal axis, we are measuring your claim, and on the vertical one, we are measuring my or your partner's claim. Both are basically numbers between 0 and 100. And the purple dot that you can see more or less in the middle is the previously described equilibrium, in which you claim 60 and I claim $40. But of course, you can ask me, what happens to the 50-50 split? And of course, if you use the previous argument, you will be able to show, to convince yourself that also the 50-50 split constitutes an equilibrium. And not only that, for example, the 40-60, the 30-70, etc. splits will also constitute equilibria of this game. Here you have a graphical representation of all equilibria in this situation. On one hand, you have a downward sloping straight line, and also don't forget that there is a dot in the upper right corner in this picture. I hope you are able to convince yourself that the situation in which both players are claiming the total 100 is an equilibrium. These equilibria are really important in game theory, but also in economics and even in political science and other fields, for example, in biology. They are called Nash equilibria. I will not show you the mathematical details today. I just listed some verbal definitions and some important characteristics of these equilibria. So let me start with the definitions. You can say that a pair of strategies constitutes a Nash equilibrium if both of you, both of the interacting parties, both of the players, do the best they can given the other's claim. Or you can rephrase this definition by saying that we are in a Nash equilibrium if none of you has incentives to claim a different amount. None of you has incentive to do something else. If you claim $60, the best I can do is $40. If I claim $40, the best you can do is to claim $60. No one has real incentives to claim any different amount. You can also think of Nash equilibria as self-enforcing agreements. For example, if we meet before interacting in this situation and we reach some sort of verbal, non-binding and non-enforceable agreement that is a Nash equilibrium, then this agreement will be self-enforcing in a sense that once we play, when we make our decisions individually and independently, we will have no incentives to break this agreement. If we agree on a 40-60 split, I will have all the incentives to claim my $40, and you will have all the incentives to claim your $60. Also, if two strategies, for example, constitute a Nash equilibrium, the beliefs behind those strategies will be self-fulfilling. Now imagine that it's not the first time that we meet each other. Now imagine that we have already met sometimes before. And let's suppose that you already have an expectation, you already believe that I'm a person who is typically claiming $40 in such an interaction. If this is your belief, you will be claiming $60, the leftover. And of course, if you claim $60, the best I can do is to claim 40. So what you expected, what you believed, is exactly what is going to happen. But you may say, just wait a second. Didn't we have too much purple in the previous graph? Which equilibrium to play when so many equilibria exist? And of course you are right. So in vain have we solved one problem and defined an equilibrium for the previous conflict situation. The next riddle is just around the corner. The previous question is indeed very interesting, very important, but unfortunately it has no easy answer. So let's talk about it some other time. If you'd like to read a little bit more about game theory without the difficult mathematics in the background, then I suggest to take a look at Schelling's game theory, How to Make Decisions. This is a book written by Dodge and published recently in 2012.